Can you hear me? Hello?
Yes, sir.
Yes, sir.
Okay, let me
Yes,
start.
sir.
The new thing, that compactness. Okay. Okay, so I'm starting compactness. I told you one time that in analysis and topology, three things are important: that compactness, Where's category theorem, this already I have taught, and the third one is connectedness. So I am teaching you this one now. Okay. After compactness, I will teach you connectedness. This is note 18. So that that you can read that compactness is an extremely useful concept both in analysis and topology. Okay. And here compactness that you won't appreciate now, but it is actually sort of topological or analytical equivalent, or you can say, and analytical from the analysis equivalent of finiteness. Briefly, if you have a finite set, really many things are there trivially. You don't need to do anything. But if you do not have a finite set, then still we can do many things by using, if we have compactness. Okay. So this, when I give you a couple of proofs of results, then it will be clear that why I said this. Now compactness is related to covering, that I taught you before. The word covering means. Okay. So for a covering, you just need to have a non-empty set. And I said this G is a collection of the notation, script G, a collection of subsets of that, means G is a subset of Px. And suppose A is a subset of X, of course X is non-empty, but A may be empty. Here I have taken E. Then suppose E is this, A is this, covered by this. Then you say that G, this one, this is the cover of A. Here in the node I have written E. So this is a cover of this. That means if you have this X, if you have this A, then members of G like this, they are covering. It need not be equal to equal, but for A, when A equal to X, then it has to be equal, because everything is coming is a subset of X. Okay. Now subcover, suppose G prime is this. That means every members of G prime is a member of this, not necessarily other way. And still you have this. Then we say that even this covers A, then we say that G, this G prime is a subcover of G, of course, for E. Okay, that I said that. But this is linear, you can define. Now, in context of topology, when you have topological space, if you feel comfortable, you can take a metric space there. But it doesn't make a difference, because we will be dealing with, again I'm saying, just open sets. You won't be dealing with even D metric, just open sets. So now what is the connection? Suppose this E or A, whatever you are taking, and this G. Suppose members of G, each one is an open set. That means G actually is a subset of tau. Remember, tau is actually a subset of power set of X. So suppose G is a subset of tau. Then we say that this is an open cover. Each member is open. That's why it's called open. So this is open cover. Okay, now the the important definition 5.2, page 152. The definition 5.2. So you are starting with the topological space X tau, and standard thing because compact, so we use usually K. So suppose K is a subset of X, and every open cover, now look, if every careful open cover, every open cover of K, of course in X tau, here it is understood in X tau, but still I'm writing in X tau means these open sets are coming from here tau. Okay, so if every open cover of K has a finite subcover, that means, what does it mean? Finite subcover. Already I have defined. Subcover means there's a subfamily will cover it, but that subfamily has to be finite. Has a, not all subcovers will have to be finite. Has a finite subcover. This is actually, we will see that eventually in the proofs, starting with an open cover, if it is given compact, then you go there, and there I am using the finite thing, and there I will show you that why it is generalization of finiteness. Through this route, actually we use the finiteness, has a finite subcover. Now empty set, look, if I take K equal to empty, then obviously every cover has a finite subcover because you have nothing to prove. Okay, it is trivially compact. But on the other hand, if you take finite set, any finite set, suppose you have this example 2, X tau, and you have a finite set. Suppose you have this. I'm saying this will be compact because if you take a cover, any cover, open cover you take, okay, that usually we write this way actually. U belongs to U. Actually, we take this, not G. We take actually U, no, script U cover, because this way you write. So if you have this, now if you take X1, it will belong to somewhere here because this is, sorry, this will be this cover. That means this is, no, actually I should not write this way. Wait a minute, because this will be covered by this. That means, wait a minute, that means I'll have to write this way. This is covered by the union. Cover is this U now, notation. Usually we use this notation when we have a topological space. Now X1 will belong to, it is here, so it is here, it belongs to the union. So some UI1, so X1 belongs to UI1 for some index, for some UI1 belongs to U. So this you can repeat for all this. So that means what will happen? That means x1, xn will belong to uik k1 to n. Look, this is a finite family. ui1, ui2, uin, and each of them is here. So this is a finite subcover. So this is a finite subcover of this K. Subcover of that actually first for K. Sometimes we write finite subcover of K, that means it is understood what is your initial cover. Okay, so this is compact. That means every finite subset is compact. Okay, because I said it is generalization of the finiteness. But a compact subset need not be finite. That I am going to show you that. That I said that. So every compact subset is finite, but a compact subset need not be finite. But a compact subset, that's a compact subset of X.
Example, closed interval in R.
Wait, come. Did not be. That you need the proof. Closed interval, why it is compact? Huh? You know the proof? It is not so easy actually. The proof uses many things usually. That I'll talk. It need not be finite. But I will give you the simpler example. It need not be finite. Before that, let's look. X tau discrete. Remember that here every subset is open. That means tau equal to this. Now look, if you take a compact set here, K compact in X tau implies this is to proof K has to be finite. K is finite. Because reason is very simple. Look, this I can take this specially, this. I am taking all these X. These are open in X. Okay, right? And of course, any X is here somewhere for some X. So this is an open cover. So this here, this is an index set also. So this is an open cover of K. But if K is compact, it will have a finite subcover. But it has a finite subcover means what? Only finitely many points. So if you say this has a finite subcover, it has a finite subcover, It means that every member of this cover is just 1 point. So it will be like this. Something xi1, xi2, like that. Points xin. It will have to be this, not more than that. That means K has to be a subset of this. That means K has to be a subset of union of this. That means K has to be finite. Okay. So in a discrete space, every compact subset is finite. But here I am just leaving a question to you that question. Suppose X tau, suppose every compact set in language is that every compact subset of X then you understand X tau is a topological space. Or you said every compact set in X tau. Sometimes you in X, but that is understood. But don't say that compact subset of that. This. That's not a right term. Compact set in X tau, suppose everything is finite. Suppose this is your hypothesis. Is tau discrete? That's the question. Think about it. Okay, that I will do later on. I will answer the question. Is tau discrete? Now the thing is that compact subset did not be finite. I said that example 3. You can take a metric space, it doesn't matter. So that X tau is a topological space. Take a sequence converging to this. Okay, in X tau. Now look, if I take A equal to this, with this its limit you are doing it, then A has to be compact. A is compact. Look, reason is, by the definition of the convergence of sequence, any open set containing, look, if you take a cover, suppose you take a cover. Then this X will be somewhere here. So there exists U naught belongs to U, to such that X belongs to U naught. Now, by the definition of the convergence of sequence, there exist only finitely many members of the sequence outside U naught. So there exists N naught such that X belongs to U naught since it converges for all xn, sorry, xn for all n greater than equal to N naught. I need to produce a subcover. Now look, only finitely many points are outside U naught. So keep U naught, and outside at best, not all of them has to be. At best you have this. Okay. These are maybe outside. These may be outside U naught. Fine. Then for each x, these points, they are here. So they are here in union. You pick up one member which contains that. Suppose this is EY1, like this is EY and not minus 1. So with this you add all these things, U naught, EY1, and that will be a finite subcover of this. That means this. This will be a finite subcover of this. That means the topological space, any convergence sequence, if you put it limit together, that will be compact. Okay. So now in particular, he was giving example of real line. You take this sequence now with this metric space. Take this sequence xn equal to 1 by n. So 1 by n goes to 0. So if I take this a equal to union 0. So this is compact. What I proved is compact in this. Here actually means the topology generated by this usual distance method. But the topological space for R you also denote by this. So here you get a infinite compact set. Okay, so a compact subset need not be finite, though every finite subset is compact. Okay, right? Now that is the example for I already did it, discrete set and that discrete topological space is finite. Now the coming back to that, okay, here there is an Heinbrohl theorem That I won't prove now, but I can tell you that what is Hein-Borel theorem. Hein-Borel theorem says in mathematics two Borels. One Borel was a recent one. He was an algebraist. This Borel is Emil Borel, who was a major theorist also. That Borel, Lebesgue, all this, he is this Borel. And this is Heinrich Heine, who gave the idea of uniform continuity. Okay, this is Hein-Borel theorem. The other Borel, this is Armand Borel. He was an algebraist, famous algebraist. Okay, but he visited India many times. But he died, I think 10-15 years back. But here I should tell you, he is a French. Though his mother tongue is French, he is not a French. He is a Swiss actually. Switzerland, a person, Swiss citizen. But actually, he worked his whole life physically in Princeton, US. Okay. Whenever he used to pass through Delhi, he used to give a lecture in IIT Delhi, Armaburn. Okay. So you say why Swiss and French? Switzerland has 4 regions. Switzerland. You can go to Wikipedia. Switzerland has divided into 4 regions. They call it cantons. And 4 cantons, they have the language. There is usually the Swiss people, they can speak in many languages. The 4 languages they speak, the region which is close to Germany. German, French, close to France, the border, and that is Italian language. It's close to, in the south of Switzerland is Italy, okay, and the west of Switzerland is France, and north of Switzerland is German. And there is another language, an old language, not too many people speak, though I say the region and that Romance. It is an version of Latin language. Okay, version of Latin language. So this French. So this Armand Borel was that type of French, Swiss French. Okay. Now, what is Hein-Borel theorem? I just diverted myself. That Hein-Borel theorem. I'm going to explain the example 5 later on. Hein-Borel theorem says, like before that, let me tell you, if you take a metric space Xt, okay, Xt metric space you take, that is metric topology, then every compact subset, this actually proposition 5.1, compact set, part of this compact set in Xt is closed and bounded. I'm giving you the background of the Hein-Borel theorem. I won't prove that, but I will give later on an easy proof of Hein-Borel theorem, which is rarely available in the literature. Now, closed and bounded. This closed right now I won't prove, because I will prove every compact set in a Hausdorff space is closed. In a Hausdorff space, but every metric space is a Hausdorff space, so that will be true. But here I will prove this is bounded. Look, in the topological space I couldn't rather define any boundedness, but for the metric space you have this. So here the result in proposition 5.1 I have proved this, and this is the result. This result I'll prove that every compact set in a Hausdorff space, that is T2 space, in a Hausdorff space star. Hausdorff space means this is Hausdorff topology is closed. A compact subset need not be closed. To be guaranteed, it has to be Hausdorff is closed. So a metric space, remember that every metric space is a Hausdorff space means what? Any two distinct points can be separated by disjoint open sets. Every metric space is a Hausdorff space. I'll prove this. Say why I don't prove this first. The reason is that there is no difference between these two proofs. The proofs are basically same. Okay, so that I will prove the more general result. Now every metric space is Hausdorff, so this will be any compact set in a metric space will be closed. And their proposition 5.1 I proved this is bounded. Now the question is that whether converse is true or not. Okay, so that compact set in a metric space is closed and bounded. Converse is that this is Heinz theorem. This, particularly that case that suppose let Xt be a metric space and K be a closed for basically any, not particular, closed and bounded set in Xt. Question is K compact. Okay. In general, the answer is no. In general. But if X is this Rn or Cn, and if you take D is the distance, Euclidean distance, you know that Rn and Cn, how it is defined, the generalization of the usual distance in R, then this is true. Then this is true. To have this, then answer is yes. That is Heinz theorem. That means Heinz theorem says that every closed bounded set in Rn or Cn is compact. In fact, Cn isomorphic because linear spacing. So isometric to R2n. So basically this is not different. This is you are applying on R2n. So answer is yes. That is Heinz theorem. Okay. So that when you go to check, actually, again I will come to the point. So while dealing with compact sets in Rn or Cn, if you are to check whether it is compact, you just check whether it is closed and bounded, because often it is not so easy to check whether a set is compact or not. So at least for negative answer, if you see that if it is either it is not closed or not bounded, then you can immediately say this is not compact. Like closed interval 0, 1, sorry, open interval 0, 1. Okay, this is not compact because this is not closed. But here I have given the direct proof of that because I have taken this cover. Look, if you take n equal to 1, this is coming this. That's an empty set. That doesn't matter. That is an extra set. So you could take n greater than 1 also. But this is a cover of it's 1 by n. N belongs to is an open cover because each of them is an open set. Open cover of this. But if you take it, look, finite subcover, you can see that it will cover only that maximum of that. That if you have finite subcover, it won't be particularly won't be able to cover. It will cover up to what? If you have a finite subcover like this, suppose this, then it will cover ultimately up to this much. Because if you take the maximum, then it will cover only this much, where M is the max of Ni. 1i. This won't be able to cover the whole thing. So this cannot have a finite subcover. It's a direct proof that this is not. In fact, this argument can be done for any set where interval where one point it is open, one side it is open. Okay, this argument can be done. Like if you have for this any kind of interval or this. Okay, right? Of course, this will be true for this also. So these are not compact. So that you can do that. Okay, so Heinberg theorem. Why? Reason is we just check it is closed and bounded. If you remember, I think part of this question I gave in minor, that I gave this, that is actually came from Heinberg theorem. So you take A, you choose a natural number such that xy belongs to R square, such that Heinberg theorem often people is enough to, they are happy to just know the statement on that. So you can use that even without bothering about the proof. If you just know it and if you can use it properly, it's fine. Okay, remember this problem that A is always closed. That you proved. One part I have given that, and B, A is bounded if and only if M is odd. Okay, that means what you are getting? A is closed and bounded if and only if M is odd. So if you use Heinberg theorem, that means A is compact. If you don't use the Heinberg theorem, you try to prove some other way, particularly using the definition. It will be difficult. I'm not sure whether you will be able to prove it. Okay, A is compact in R square, the usual distance, of course. If and only if M is odd. Okay, so that's why I gave you this problem. But actually, the idea behind, the motive behind that problem is this result. Okay, A is compact in R square if and only if M is sorry, is bounded. You are not telling me that. I was making a mistake in that. Huh? Sorry. Bounded. It is even. Already know that. You get an odd degree polynomial, you get a root on that. So A is bounded if and only if M is even. So this is important. If proved. So this is compact if and only if M is even. Okay. So that is the importance of Heinberg theorem. Just an example I am giving you that. And this example later on you'll see that it is very important. Okay. Now the thing is that how to prove that a compact set in a metric space is bounded. You can prove it in straight and that, but particularly the what I have given you the proof. Okay, so that in a metric space proposition 5.1, every compact set, right now I'm proving it, that in a metric space Xt. Of course, I can assume this is non-empty because empty set is always bounded. Is bounded. Okay. So look at the proof. Okay. Proof, first of all, choose any point in x0 belongs to this x. Okay. Now you choose any point x belongs to k, suppose. Actually, for any x it will be. Then there exists. Okay. So actually, I don't need this. I can just take this thing. To take this, so dx(x0), so by the definition of metric space, it will be a number, real number. So there will be some n. Okay. For some n belongs to n. That means what? That means x can be covered by this. Look, if I take this, I am writing equal because my whole set is x. So you take any x, that will be less than this. This means what? This means x belongs to b x0 n. This is here, right? Okay. So this is always true. Now k is a subset of x. Now if k is compact, this is, look, each of them is an open ball, so it's an open set. So this is an open cover. So this is an open cover of k. Now if k is compact, it will have a finite subcover. Here the index set is this. So there exists n1 nk belongs to n such that the subcover k will be this. Now look, center is same, so that if you have taken a bigger integer, that will be contained in this. So if I take m equal to this max of ni, in fact I not necessarily need max, I need an integer, choose an integer greater than this, everybody here, but one this, then this will be equal to actually sorry, I don't need this. The union okay. B x not n. Okay. So k is contained in this. The idea of the boundedness is precisely this. That it can be contained inside a ball. That actually got. Okay, hence k is bounded. So that unless it is bounded, it won't be compact. Okay. Like R, look here, is itself is not compact because R is not bounded. Okay. So these I got. This I was telling that in a Hausdorff space, every non-empty compact subset is closed. I have taken non-empty because if it is 5, 5 is always closed. Okay, right? Now, look, proof is not difficult, but only you should understand the idea. Proof is actually easy. Okay, so let me explain that. You should read the proof yourself again. Proposition 5.2. Here the hypothesis is, I am writing hypothesis is given. X tau is a Hausdorff space. And K, because if it is empty set, nothing to prove. I won't go for the trouble. So that K is a non-empty. This is this, and K compact. That means K is a non-empty compact set, and this is Hausdorff. These two are hypotheses. And the conclusion. Is closed in X tau. That means X minus K is open. Okay. Hausdorff, you should remember that means whenever you have two distinct points in X, XY distinct points, there exist open sets. This is definition. Open sets U and V in X tau such that X belongs to U, Y belongs to V, and UV are disjoint. There exists. Okay. And Y metric space is Hausdorff. If you take this X not equal to Y in a metric space in X3, then you take 2R equal to dxy. Dxy is, since X not equal to Y is greater than 0. Then you can check that PXR intersection BYR by triangle inequality. You can prove that. This is 5. Here Y belongs here, X belongs here. So every metric space is a Hausdorff space. Okay, that's what I'm doing. So basically, I need this thing. Okay, nothing else. Look how I am going to do it. Okay. Well, if you want to prove closed, that means what? Remember that a set is closed A bar if and only if A bar equal to A, right? So that if you can show no point outside A, suppose if you show that X doesn't belong to A, implies if you show it, I'm not, X is not a closure point, X doesn't belong to A bar. Okay, then it is done. Basically, if you show that A bar is this, actually contained in this, because by definition, A is always contained in A bar. So if you show that, that means you will be showing this. But which means what? That means any point outside A is not a closure point of A. This. Okay, but any closure point of A must be inside A. That I need to prove. Okay, that exactly I'm going to prove it. That any point outside K compact set is not a closure point of this. Closure point, that means not a closure point means what? I'll have to show. Remember that. That means I'll have to produce an open set containing that which won't intersect A. Okay. That any point that actually will show that any point lying outside K is not a closure point of C. That's it. So that look proof. Take a point outside this, and I will show this is not a closure point. How will I show that? I will produce an open set containing A, that is a neighborhood of A which won't intersect K. Okay, fine. Now look where I am using Hausdorffness. Okay, choose any X belongs to K. Choose. Okay, now X belongs to K and A doesn't belong to it, implies A doesn't belong to K. So that A and X are distinct points. A you have picked up from outside a point, outside the compact set K, and keep it fixed. Okay, you pick up arbitrarily and then you keep it fixed. Then you are not changing. Because I want to show any point outside K is not a closure point. So pick up a point outside A, K, and then you keep it fixed. Now look, a not equal to x, so they are distinct points. Now I will use the house graph. That means there will exist an open set containing a, and there will exist a containing an open set. There will exist an open set containing x, such that they are disjoint. Now look, a is fixed for the time being. Only x will be changing. So there exist open sets ux and vx, of course in x tau, such that a belongs to ux, okay, and x belongs to vx and ux intersection vx equal to phi. Look, if you do it for metric space, you will be only taking balls here, open balls. You will get that, but otherwise there won't be any difference. Okay. Now look, so here I am using the Hausdorff-ness. This is the only place I will be using Hausdorff-ness. Okay. You can see the entire proof that where I am using Hausdorff-ness, just this here. But point is, this is critical because I have given the counter example. I said that where you can find a counter example. Okay. If it is not Hausdorff's Ax, then this statement need not be true. This theorem won't be true. Now look, this process I can repeat for each x. That means what you are getting? I will get this. Look, that means Vx, x belongs to k. K I am using as an index set. This is an index set also. For each x belongs to k, I am getting a Vx. Okay, so Vx is an open set containing x. So this is an open cover. You don't need to mug up the proof, but you should understand the proof. This is an open cover of k. But k is compact. So it has a finite subcover. Finite subcover means what? You have the index at this k. That means it will have finitely many points here, finitely many indexes here. So that means there exists x1, xn in k, such that k is contained in k is a compact set, k is also I am using as index set. So it has a finite subcover. Since k is compact, that I have not written. Since k is compact, it will have a finite subcover. So there exists. You can write since k is compact. Since k is compact, there exists an open cover. Okay, there exist finitely many points. Now you see that for each xi, consider uxi. That means A belongs to this. Corresponding this each vxi, you have uxi, but uxi contains A, so their intersection will also contain A. So you take this, say, okay, I'll call it V. Say, look, it is finite union of open sets, so this is open. Look here, this is open set because finite intersection of open sets. Here, be careful, the finite. If I had arbitrary intersection, it need not be open. So it is open. Okay. So what I got? I got A belongs to U, K subset of V. Now you see that what I want to prove that U intersection V is empty. Well, how to do that? Well, U is, remember that U is this. V is this. ठीक है? Now U intersection V. Okay. पहले Look, I will use the distributive law. So you do it this one way. Just don't open everything right now. So this will be union I 1 to n u intersection phi xi. Okay, but u is this. That means u is a subset of uxi. That means this is look, the way I have constructed, I use the Hausdorff. Each of them is equal to phi. The union of this is phi. So this is a subset of phi. So this is phi. Okay. So I have proved u intersection v is phi. But remember that A belongs to u, k subset of phi. U intersection v is empty. That means u intersection k is empty. Got it? U intersection k is empty. But U is an open set containing A. It implies A is not a closure point of K. That means A doesn't belong to K bar. I am done. Okay. That means any point outside K is not a closure point. Now look where actually I used that I told you that where I used finiteness. But suppose if I didn't have compactness, okay, then what will you do? Look, then you will take what will be a choice. There V is not a problem. That you could take even V, union of Vx, a Vx, x belongs to K, it will be open. But you will have to take this. Okay. Look, every argument, whatever it will work. U will be, A will be here because A is in each Ux. So A will be here. V is open. But look, only problem is that it is an arbitrary intersection of open sets. It need not be open. In the whole argument, you see that where you used compactness. I was looking for finite subcover. That means ultimately this one I needed. So I could claim that immediately this is an open set. But otherwise, you'll have to write this way. But there is no guarantee it will be open. So that here you are having finiteness. That's why I said, if you had any finite collection in the beginning, you have the whole argument will be valid. But only if you have compactness, you need every open cover as a finite subcover. That means what you are doing, that compactness is a generalization of finiteness. Read the proof again carefully. Whole proof related to this. Here is no guarantee it will be open. Here it is guaranteed. Compactness is giving the guarantee that this will be open. How? Because I know only every finite intersection of open set is open. So I needed from compactness, I needed to switch to finite. Okay, that's why I said that compactness is a generalization of finite set. Actually, here, look at this. Warning, the proposition 5.1 is not true unless one assumes this is. You should look at the problem, page 65 of the Alipantis-Barkinson book, problem number 21. I said you don't need to solve the problem, but it will be good if you understand what the problem is saying. But in the next semester, you need to solve the problem. Okay, right? And corollary, I said because metric space is Hausdorff. Now the remark I said that you should, what I was shouting at, that is written at remark. Understand? Remark after warning. Read the proof of proposition 5.2 very carefully and see actually where we have used the compactness of K. To take U equal to intersection, whole intersection, everything works except that U may not be open now, being an arbitrary intersection open set. Note here how we have turned compactness into finiteness. This proof is an example of validating my observation in the beginning of this chapter. Compactness in some sense is a topological generalization of finiteness. Okay. I'll do a couple of more results. I'm coming back after 10 minutes. Okay. Because next Saturday I may not take the class on that. I will take the class up to next Friday. Anyway, so I'm coming back after 5-10 minutes. Hello, should I start? Hello?
Yes, sir.
Okay. I just do a couple of theorems, but this chapter you should read very carefully. That look, proposition 5.3, it is saying, basically briefly it says, a closed subset. Suppose you have a X star set, a closed subset of a compact set. Because already you have compact set is compact. This is the result actually. The proof is easy actually. Once you understand the definition of compactness well, it's very straightforward. That means what I'm doing, suppose you have this X, this is F, this is compact, this is closed. Then I am claiming, this is your hypothesis, then I am claiming this will actually be compact. That means I'll have to show. Right now basically do not have anything about compactness other than the definition. That means I'll have to show that every open cover of F has a finite subcover. So you take this. Where UI is an open cover of this. Each UI is open. I'll have to show this is a finite subcover. Okay. Now look where I will be using closeness. In fact, even if a small result, you should see that where you are using your hypothesis. Okay. If you are not using one hypothesis, I think I told you before. Again, I am repeating it. If you are not using some hypothesis, there are two possibilities. Either you don't need hypothesis, that means you can strengthen your result, or else your proof is wrong. So look here, closed thing. That means X minus F is open. Okay. Now look, F is covering this, and this is itself open. So this is covering its complement. That means whole X, look, whole X is this, F union X minus F. F is covered by this, and X minus F is this. So that means X will be union to Y. Here I am writing whole set, that's equal. I belongs to I union X minus F. It's very simple. I am just using the definition. But X is not given compact. In fact, if X is given compact, it will be same proof will be there. Here I have taken K. K equal to X will be the particular case. But K is a subset of X and K is compact given. And here you look, everybody is open here. So this is an open cover. This together with this. It is an open cover of K. This is an open cover of K. So this is an open cover of K. This one, right? But K is compact. So it will have a finite subcover. So that, look, finite subcover means there exists I1, I2, In belongs to I such that K this. Look, this one I may need, may not need. All I knew that will have a finite subcover. But here I am keeping it because I do not know whether I require it or not. But from other, which is an arbitrary collection, it will have finite. So altogether it will be finite. Look, if it is already a cover, if you add one more thing, that will still be a cover. So it may be there, may not be there. Okay, required. Okay, but since I do not know, I am keeping it. So this will be this. Okay, now look. So F is a subset of K. Okay, this argument. Now very simple. Now look, so F is being covered by this. But now look, X minus F only cover this X minus F. It can't cover F, any part of F. So that means F has to be covered by this. F is a subset of K. K is covered by this. But this one cannot cover any point of F. So that I must have but that was the finite subcover of that. It is done. That's it. So F is compact. So any closed subset of a compact set is compact. Proposition 5.4 already I said that. Actually, no, not already. Actually, I proved something more than required. That you should read the comment and then. Okay. So I should have put this proposition 5.4 before proposition 5.3 actually. Okay. Right. Now, so that any closed subset of a compact set is compact. Okay. Next result, that how it behaves regarding continuous functions. Look, I said when I was defined continuous function, I said actually it's a vehicle to move. It's a vehicle to move one space, to move from one topological space to another topological space. So that is the thing. That's it is this. I said continuity. It should behave nicely. Now look, suppose you have a continuous function between two topological spaces. If you feel comfortable, you can take them metric space. It doesn't change the argument. Suppose this is continuous. Now suppose I have A is here, A is compact. Given. Now I am moving here, they fail. I moved by this continuous function. Here it was given compact. Will it have the same property here? That means is it compact here? Proposition theorem 5.5 is saying yes, it is. There usually we say this result briefly like this. Continuous image of a compact set is compact. Continuous A, because it doesn't matter which continuous map you're taking. A continuous image. This is image, continuous image of a compact set is compact. Well, proof is very straightforward. You start with the open cover of this. Okay, take open cover here. Since it is Y, you take this. I belongs to I. That means Vi is an open cover. So each Vi is open in Y sigma. Okay. Now we'll be taking this. Look, A is F inverse, FA. Now look, this is a subset. I will when we go, because if it is not one to one, look here, what is can happen? X, this is X, this is Y. Suppose this is your A. So I am getting FA. But when I'm coming back, FA inverse, of course, by definition, I will get all the points of A. But if it is not one-to-one, some point of like here, it could go here also, right? So when I take inverse, this point will also come. So this will be a superset of that. That's why it will be subset of that. You should write, be careful, you write that. Don't write equal. It will be equal if and only if it is one-to-one. Okay, right? So that this is I am writing. So this is true. I'm just applying F inverse on both sides. F inverse FA of this will be subset of this. Look, F inverse will be same as this. It is not a problem. Here I should make a comment on that. That F inverse, this is always true. Sorry. This is always true. Look, F inverse problem nahi hai. F only F in will be a problem. Like if A intersection B, it need not be this. This will be FA intersection FV. Union में भी problem नहीं है. Equal it will come. Okay. Only this will be this. That FA intersection B will be contained in this. Okay. It need not be equal. Okay. But for inverse, it is not a problem. Inverse, it will be always come equal. Okay, like this. Okay. If you take intersection here, it will come intersection. So now look what happened. Look at the beginning here and here. Now remember, I have not used continuous anywhere yet. But if you look at the equivalent conditions of continuity, it is a global continuity, continuity on whole X. There, equivalent condition, one important equivalent condition is that inverse image of an open set is open. Here each Vi is open in Y sigma. Since F is continuous, is open in X tau. Got it? Because F is continuous. Because F is continuous. That means what you are getting? That means you are getting this. A subset of this is, and each of them is open. So this is an open cover of A. But A was given compact. So it will have a finite subcover. So that means there exists I1, In such that belongs to I actually, such that A this. Here I am using compactness. Now I go back to FA. So FA will be contained in this F of this. I told you that only problem is that intersection. Here it is union. So this will be union F inverse V I K 1 to n. But be careful here. I can't write equal to VIK. It will be a subset of VIK because if it is not onto when you come back, look, you have this. Okay, suppose your whole image X, this goes up to this, but VI has some point from here. So when you come back, like here, simple thing, you get X, so F inverse Y, like suppose you are getting this, okay, right? Let me this VIK, suppose VI, okay, suppose. Suppose this is not onto, and suppose this is a Vi is this. Okay, and its image is Ui. Okay, suppose Vi actually you are getting like that, so that when you take F inverse Vi, you are getting Ui, but when you take Fui, you are taking image, then this part you won't get back because this is not in the image anyway. So whole image was this and Vi was this, so you will get a content in Vi. So that means, but that doesn't make a problem with my argument. But you should be careful, you should not write equal, because each of them will come subset. Union Vi, then K, this is K 1 to N. Now look, ये सब भूल जाओ, देखो FA here I tried with an remember that I started with this in the previous page. देखो ये ठीक है, I started with an arbitrary open cover here. Okay, now look what I have produced. FA is contained in this, so it's a subcover. So I have produced a subcover of this, so that FA is compact. Continuous image of a compact set is compact. Got it? Okay. Right? Okay, fine. Just look at just conclusion on that before stating the next result. Want to bring back soup and that. I'm just making this thing comment. Remember that if you take real valued function, suppose this is continuous, okay, and D. So you get FA. Suppose A is compact. So this, by the result I proved this is compact. But already I proved in a metric space it is closed and bounded. But in a Hausdorff space I proved in Yang this is bounded. Okay? So first of all, this image set will be bounded. That's the first conclusion. Okay, you got it. This remark I put the star. You should read it. This is basically analysis. Okay, compact, closed, and bounded. That means soup of FA and inf FA, they are real numbers. Okay, but also I commented soup of FA for any bounded set in R. If you take a bounded set in R, then soup B actually is a closure point, belongs to B bar. Similarly, inf V belongs to B bar. If B is bounded, in fact, separately you can do that. If it is bounded above, the soup B will be a closure point. By the definition of supremum, that result you got epsilon that you used in minor. Similarly, infimum, if B is bounded below, inf B will be here. The soup FA, that means since FA is bounded, so it will be first of all closer. But this is closed. So this is FA. That means soup FA belongs to FA. Similarly, inf FA belongs to FA bar equal to FA. What does it mean? When supremum belongs to the set, we call it max. That means max of FA exists, and that is in similarly minimum of FA exists. That means it means what? It means there exists A belongs to A such that Fa equal to, I can write max of fx, x belongs to A. That means supremum is obtained. It is called supremum is obtained as a value. Supremum is obtained as a value. Supremum of Fa is obtained as a value, that is max. Similarly, there exists, you can take A1, there exists A2 belongs to A such that Fa2 will be minimum of Fx, x belongs to A. Sorry. That means if you have a real valued function, there I took between two topological space functions. But if you range your real line, that means if you take a real valued continuous function on a topological space, then for any compact subset, image will be closed and bounded, and as an implication, you will get that it will have maximum and infimum. That means maximum infimum will be obtained as functional values. That exactly I pointed. Okay, both supremum infimum. Okay, if A is closed and bounded, then both sup infima A in itself. That means bounds are attained. That means what we are saying. That means any continuous real valued continuous function, any real valued continuous function on a compact set is bounded. And not only that, bounds are attained. That means as functional values. That I did. Okay. So I will rest I'll do tomorrow. Okay. That means tomorrow's theorem. Oh, that exactly I proved. Theorem 5.6. Okay. I didn't realize that. This is theorem 5.6 and I put a star marks. That exactly I proved. Okay. Right. So I will start from theorem 5.7. This is theorem. What I proved, I didn't realize. I was making a comment that I proved theorem 5.6. Okay. Right. Okay. I will see you tomorrow this time. Okay. 12 o'clock. 12 noon. Fine. Okay. Bye.
Thank you, sir.